Hello students, today let us study about the topic soil chemistry and fertility under the main subject agrochemical and pest control. Soil is the collection of natural bodies on the earth's surface, in places modified or even made by man of earthy materials containing living matter and supporting or capable of supporting plants out of doors. Its upper limit is air or shallow water. At its margins, it grades to deep water or to barren areas of rock or ice. Its lower limit to the not soil beneath is perhaps the most difficult to define. Soil includes the horizons near the surface that differ from the underlying rock material as a result of interactions through time of climate, living organisms, parent materials and relief. Hence, in this episode, the following aspects are going to be seen. They are physical properties of soil, ion exchange of soil, pH of soil, oxidation reduction of soil and fertility of soil. Let us study about the aspects one by one. The first aspect, physical properties of soil. Under this, we have different properties. They are horizonation. Soil horizons are discrete layers that make up a soil profile. They are typically parallel with the ground surface. In some soils, they show evidence of the actions of the soil forming processes. 6 soil horizons are commonly recognized and are designated using the capital letters O, A, E, B, C and R. Let us study about these horizons one by one. O horizons. O horizons are dominated by organic material. Some are saturated with water for long periods or were once saturated but are now artificially drained. A horizon. A horizons are mineral layers that formed at the surface or below an O horizon that exhibit obliteration of all or much of the original rock structure. E horizons. E horizons are mineral layers that exhibit the loss of silicate clay, iron, aluminium, humus or some combination of these, leaving a concentration of sand and silt particles. These horizons exhibit obliteration of all or much of the original rock structure. B horizon. B horizons are mineral layers that typically form below an A, E or O horizon and are dominated by obliteration of all or much of the original rock structure and show one or more of the following, that is alluvial concentration of silicate clay, iron, aluminium, humus, carbonate, gypsum or silica alone or in combination. Evidence of removal of carbonates, residual concentration of sesquioxides, coatings of sesquioxides that make the horizon conspicuously lower in value, higher in chroma or redder in hue than the overlying horizons without apparent elevation of iron. Alteration that forms silicate clay or liberates oxides or both and that forms granular, blocky or prismatic structure if the volume changes accompany changes in moisture content or brittleness. The C horizon. C horizons are mineral layers which are not bedrock and are little affected by pedogenic processes and lack properties of O, A, E or B horizons. The material of C layers may be either like or unlike that from which the overlying soil horizons presumably formed. R horizons. R horizons are the layers of hard bedrock. Next, moving on to the soil color. In well aerated soils, oxidized or ferric iron compounds are responsible for the brown, yellow and red colors you see in the soil. When iron is reduced to the ferrous form, it becomes mobile and can be removed from certain areas of the soil. When the iron is removed, a grey color remains or the reduced iron color persists in shades of green or blue. Upon aeration, reduced iron can be reoxidized and redeposited, sometimes in the same horizon, resulting in a variegated or mottled color pattern. These soil color patterns resulting from saturation is called redoxymorphic features, can indicate the duration of the anaerobic state, ranging from brown with a few mottles to complete grey or glaciation of the soil. Soils that are dominantly grey with brown or yellow mottles immediately below the surface horizon are usually hydric. Soil color is typically described using some form of color reference chart such as the Munsell color chart. Using the Munsell system, color is described in reference to the colors, hue, value and chroma. Next, moving on to the soil texture. Soil texture refers to the proportion of the soil separates that make up the mineral component of soil. These separates are called sand, silt and clay. These soil separates have the following size ranges. Sand, which is equal to less than 2 to 0.05 millimeter, silt, which is equal to 0.05 to 0.002 millimeter, and clay, which is equal to less than 0.002 millimeter. Sand and silt are the inactive part of the soil matrix because they do not contribute to a soil's ability to retain soil water or nutrients. Because of its small size and sheet-like structure, clay has a large amount of surface area per unit mass, and its surface charge attracts ions and water. Because of this, clay is the active portion of the soil matrix. For all mineral soils, the proportion of sand, silt and clay always adds up to 100%. These percentages are grouped into soil texture classes, which have been organized into a textural triangle. Next, moving on to the soil structure. The soil separates can become aggregated together into discrete structural units called beds. These beds are organized into a repeating pattern that is referred to as soil structure. Between the beds are cracks called pores through which soil, air and water are conducted. Soil structure is most commonly described in terms of the shape of the individual beds that occur within a soil horizon. The shape of the beds may be granular, platy, blocky, prismatic, columnar, massive or single grain. Let us study about the structures one by one. Granular. They are roughly spherical like grape nuts, usually 1 to 10 millimeter in diameter. Most common in A horizons where plant roots, microorganisms and sticky products of organic matter decomposition bind soil grains into granular aggregates. The next structure is platy. Flat beds that lie horizontally in the soil. Platy structure can be found in A, B and C horizons. Next is blocky. They are roughly cube shaped with more or less flat surfaces. If edges and corners remain sharp, we call it angular blocky. Sizes commonly range from 5 to 50 millimeter across. Blocky structures are typical of B horizons, especially those with high clay content. They form by repeated expansion and contraction of clay minerals. The next structure is prismatic. They are larger, vertically elongated blocks, often with 5 sides. The sizes are commonly 10 to 100 millimeter across. Prismatic structures commonly occur in frangipans. The next structure is columnar. The units are similar to prisms and are bounded by flat or slightly rounded vertical faces. The tops of columns, in contrast to those of prisms, are very distinct and normally rounded. The next structure is massive. They are compact, coherent soil not separated into beds of any kind. Massive structures in clayey soils usually have very small pores, slow permeability and poor aeration. Next is single grain structure. In some very sandy soils, every grain acts independently and there is no binding agent to hold the grains together into beds. Permeability is rapid, but fertility and water holding capacity are low. Next is consistency of soil. Soil consistency is the resistance of a soil at various moisture contents to mechanical stresses or manipulations. It is commonly measured by feeling and manipulating the soil by hand or by pulling a tillage instrument through it. The consistency of soils is generally described at 3 soil moisture levels. They are wet, moist and dry. Consistency of a soil sample changes with the amount of water present. Such change in soil consistency may be accurately measured in the laboratory following standard procedures which determine the Etterberg limits. This limit corresponds to the moisture content at which a soil sample changes from one consistency to another. Two of the Etterberg limits are important. They are liquid limit and plastic limit. Moving on to the second aspect, that is ion exchange of soil. As soils are formed during the weathering processes, some minerals and organic matter are broken down to extremely small particles. Chemical changes further reduce these particles until they cannot be seen with the naked eye. The very smallest particles are called colloids. The mineral clay colloids are plate-like in structure and crystalline in nature. In most soils, clay colloids exceed organic colloids in amount. Colloids are primarily responsible for the chemical reactivity in soils. The kind of parent material and the degree of weathering determine the kind of clay present in the soil. Since soil colloids are derived from these clays, their reactivity is also influenced by parent material and weathering. Each colloid has a net negative charge developed during the formation process. This means it can attract and hold positively charged particles. An element with an electrical charge is called an ion. Potassium, sodium, hydrogen, calcium and magnesium all have positive charges. They are called cations, and ions with negative charges such as nitrate and sulfate are called anions. Negatively charged colloids attract cations and hold them like a magnet holds small pieces of metal. This characteristic explains why nitrate is more easily leached from the soil than ammonium. Nitrate has a negative charge like soil colloids. So, nitrate is not held by the soils but remain as a free ion in soil water to be leached through the soil profile in some soils and under some rainfall conditions. The charges associated with soil particles attract simple and complex ions of opposite charges. Thus, a given colloidal mixture may exhibit not only a maze of positive and negative surface charges, but also an equal complex complement of simple cations and anions such as Ca2+ and SO4 that are attracted by the particle charges. The adsorbed anions are commonly present in smaller quantities than the cations because the negative charges generally predominate on the soil colloid. Cation exchange is an important reaction in soil fertility in causing and correcting soil acidity and basicity, in changes altering soil physical properties, and as a mechanism in purifying or altering percolating waters. The plant nutrients like calcium, magnesium and potassium are supplied to plants in large measure from exchangeable forms. Moving on to the third aspect, that is pH in soil. Soil pH directly affects the life and growth of plants because it affects the availability of all plant nutrients. Between pH 6.0 and 6.5, most plant nutrients are in their most available state. A nutrient must be soluble and remain soluble long enough to successfully travel through the soil solution into the roots. Nitrogen, for example, has its greatest solubility between soil pH 4 and soil pH 8. Above or below that range, its solubility is seriously restricted. Let us study how pH affects nutrients, minerals and growth. The effect of soil pH is great on the solubility of minerals or nutrients. 14 of the 17 essential plant nutrients are obtained from the soil. Before a nutrient can be used by plants, it must be dissolved in the soil solution. Most minerals and nutrients are more soluble or available in acid soils than in the neutral or slightly alkaline soils. A pH range of approximately 6 to 7 promotes the most ready availability of plant nutrients. But some plants such as azaleas, rhododendrons, blueberries, white potatoes and conifer trees tolerate strong acid soils and grow well. Also, some plants do well only in slightly acidic to moderately alkaline soils. The soil pH can also influence plant growth by its effect on activity of beneficial microorganisms. Bacteria that decompose soil organic matter are hindered in strong acid soils. This prevents organic matter from breaking down, resulting in an accumulation of organic matter and the tie-up of nutrients, particularly nitrogen, that are held in the organic matter. Moving on to the fourth aspect, that is oxidation reduction of soil. In soil systems, rapid changes in moisture content strongly affect soil aeration status. In addition to changes in bulk conditions, there are microzytes or zones where diffusion of oxygen is restricted, such as small pores filled with water and the interior of aggregates where oxygen consumption is more rapid than oxygen diffusion. In areas where there is better access to soil air and pockets of easily decomposed organics and intense decomposition can deplete available oxygen and produce a number of redox active organic compounds. From a global perspective, redox is an important aspect of energy and carbon transfer. Carbon reduction and its subsequent oxidation fuel the biological world. Carbon reduction or gain in electrons is often called photosynthesis by the uninitiated, and the reverse oxidation reaction is called respiration when applied to humans and other large animals. Microbial respiration accompanies or is synonymous with mineralization. Regardless of your perspective, redox reactions are important aspects of soil chemistry. Redox reactions change the speciation and solubility of many elements, create new compounds and alter the biochemistry of soils. In a complex mixture such as soils, the interpretation of redox relationships is difficult, since the dynamics of soil oxygen, which drives the changes in redox potential, are rapid, equilibrium may not be attained. From a thermochemistry viewpoint, redox is not at all equilibrium, because all of the energy yielding compounds by definition contain excess free energy and are unstable with respect to carbon dioxide and water. Processes which reduce oxygen levels and decrease redox potentials are driven by microbial consumption of oxygen. Conditions necessary for lowering redox potentials include a source of decomposable organic material, a population of microbes capable of utilizing this energy source for metabolism, and a restriction on the resupply of oxygen. These requirements are not uniformly distributed in soils and sediments. Thus, redox reactions and redox potentials are not uniform throughout the soil matrix. In fact, redox potentials are highly variable and therefore are best used as an indication or relative status of the soil. Moving on to the fifth aspect, that is fertility of soil. The ability of the soil to supply essential plant nutrients and soil water in adequate amounts and proportions for plant growth and reproduction in the absence of toxic substances which may inhibit plant growth. Soils are composed of 5 main components. They are: the first component, mineral particles derived from rocks by weathering. Second component, organic materials, humus from dead and decaying plant material. Third component, soil water, in which nutrient elements are dissolved. The fourth component, soil air, both carbon dioxide and oxygen. The fifth component, living organisms including bacteria that help plant decomposition. Soils differ because they have different proportions of these components and because the mineral particles have been affected to different degrees by weathering. Age of soil minerals, prevailing temperatures, rainfall, leaching and soil chemistry are the main factors which determine how a particular soil will weather. Vanuatu soils, because they are geologically young, are often less weathered than soils of neighboring Pacific countries. The major and micro or trace elements are made available to plants by breakdown of the mineral and organic matter in the soil. Availability of these nutrients depends on how much is present, the form in which it is present in the soil, the rate at which it is released from organic matter or mineral particles, and the soil pH, that is, its alkalinity or acidity. The proportion of nutrients held on the clay and humus particles influence deficiencies. For example, potassium, calcium and magnesium are held on the surface of clay particles and are directly taken up by plant roots or from the soil solution. An excess of potassium can create a deficiency of calcium or the reverse can occur. Acid soils high in manganese often cannot supply enough cobalt for rhizobium bacteria, with a consequent effect on nitrogen fixation by the legumes. Also on very acid soils, manganese and iron make phosphorus unavailable to the plants by fixing it in insoluble complexes. The chemical relationships influencing soil fertility are complex and affected by the parent material from which soil develops. The type of clay present, the proportions of different sized particles, example sand, silt, clay, which also have an important effect on the soil structure. Finally, to conclude with today's topic, soil is the top layer of the earth's crust in which organic matter grows. There are many components which determine a soil type, such as the pH, nutrient level and organic content. These factors can vary depending on the type of plant or crop which grows in the soil and also on geographic locations. Thank you.